Okay, so we're doing problems from chapter 13. So this problem says a 50-turn coil has a diameter of 15 centimeters. The coil is placed in a spatially uniform magnetic field of magnitude 0.5 Tesla so that the face of the coil and the magnetic field are perpendicular. So there's the coil and there's the magnetic field. Find the magnitude of the EMF induced in the coil if the magnetic field is reduced to 0 uniformly in 0.1 seconds, okay, 1 second and 60 seconds. So I'll just do part 1. EMF induced in the coil, that's the voltage induced in the coil because of the induced EMF. Okay, so what will be the direction of the induced current? So the magnetic field is decreasing. The induced current should be such that it's opposing it. It's want to produce a magnetic field in that direction, and it'll be in this direction. Okay. So the induced current will be in that direction. So the electric field is in that direction. This is Lenz's law. This is Faraday's law. And the magnetic field is B area dt. And so the magnitude of the induced EMF, the area is not changing. It's del B times area. Well, the final field is 0, so B final minus B initial. So initial field divided by delta T pi r squared. 0.5 Tesla, and we're going to make it 0 in 0.1 second. Pi r is 7.5 centimeters. Yeah, that's 10 to the minus 4. So, and this is 5 times pi times 7.5 square into 10 to the minus 4 volts. .289 volts. Okay, so here's why we do something like this. So this is a strong field. Where do you encounter a strong field like this? In an MRI machine. Okay, you just can't shut down the MRI machine just like that. If the field went to 0, okay, so here's a nearby circuit somewhere. You have this current induced in that circuit, and maybe it'll turn something on, or okay, it might induce a current in something that you don't want. Okay. So if you have large magnetic fields, you don't quench meaning make it go to 0 fast. Okay. You do it slower and slower. Okay, A single turn circular loop of wire of radius 50 millimeters lies in a plane perpendicular to the spatially uniform magnetic field. During a 0.1 second time interval, the magnitude of the field is increased from 200 to 300 millitesla. Determine the EMF induced in the loop. If the magnetic field is directed out of the page, what is the direction of the current in the loop? Okay, we'll figure out the direction first. So you're increasing the magnetic field. The induced loop current should be such that it's opposing that, so you want to produce a magnetic field like that. So the induced EMF current is in that direction. Okay, B was increasing. Okay, so Mr. Faraday tells us, okay, and this is equal to minus d by dt of B times area. So the magnitude of the induced EMF is area times del B by R is 50 millimeters. Delta B is 300 minus 200, 100 millitesla. And this change happens over 0.1 seconds. So the induced EMF is, so this is 10 to the minus 1, that's 10 to the 6, and we'll make that 5, 50, 50 pi into 10 to the minus 6 volts. Oh no, 50 squared, so all right, that's 10 to the minus 1, which cancels with that. That's 10 to the minus 6, 2,500 pi. Okay, so 7.85 millivolts. So here you want to use Lenz's law to determine the induced current in each case. Okay. So here the magnetic field is coming out of the sheet, and if you move to the left, the magnetic flux coming out is decreasing. So you want to increase that. So you want to produce a magnetic field in this direction. So the induced current should be like that. Okay. So the induced current okay, so field is coming out, and to me this looks like the plane is parallel to the magnetic field. So when you move this, the flux is not changing. Induced current is 0. Same thing here. The flux is not changing. Yeah. Okay, this is easy. This is moving in the opposite direction, so the induced current is in that direction. Okay, you're moving this string like that. What is happening?
The flux is increasing.
Flux is increasing. So you want to produce a flux into the sheet. So the induced current is in this direction. Yep. Stick your fingers in the direction. Yep. How long is that current induced?
Until removing the flux doesn't change.
Yeah, so once the string is completely in, now the flux is not changing. Okay? And so the induced current, so it's increasing the fastest when half of the ring is there. Okay? At that time the peak current is at the peak, and once it gets like that, the current has gone to zero. Here the flux is decreasing, so again the induced current is in this direction. Okay. A coil of 1,000 turns encloses an area of 25 centimeters square. It is rotated in 0.01 seconds from a position where its plane is perpendicular to the Earth's field to one where it's parallel to the field. I guess so. Okay. So the induced EMF is d by dt of n. N is the number of turns times b times a times cosine theta. Okay, so here theta equal to 0, here theta equal to 90. So what is changing this time is theta. And this change happened over 0.1 second. The initial angle was, theta initial was 0 degrees. Final angle was 90 degrees. So this is 1. So the induced EMF, I'm going to go to the next page. Cosine 0 degrees, 0.01 second. It was 1,000 turns. Area is 25 centimeters square. Cosine 0 is 1, 10 to the minus 2 seconds. All right, 10 minus 9, 10 minus 7, 10 minus 4. So 10 minus 4 volts, 6 times 25. And that's 150, so 15 into 10 minus 3 volts. Okay, 15 millivolts. And again, see, it's 15 millivolts is induced. How long is it induced for?
0.01 seconds.
Okay, so for 10 milliseconds. The rod shown is moving through the uniform field of strength 0.5 Tesla with a velocity of 8 meters per second. Okay. 8 meters per second. Is that fast?
Kind of.
Yeah, Usain Bolt runs at 10 meters per second. Okay, so it's about 20 miles an hour. What is the potential difference between the ends of the rod? Which end of the rod is at a higher potential? Okay, so let's first figure that out. Okay, so let's look at a positive charge moving in this direction. The field is, so force on the positive charge is QV cross B. V cross B, if you turn the force on it is downwards. So this end will be positive, this end will be negative. Okay. All right, and the EMF induced is BLV. So the magnetic field is 0.5 Tesla. L is 5 centimeters. Okay, so we'll make that 10 to the minus 3, 25 times 8, 200 millivolts. A 25 centimeter rod moves at 5 meters per second in a plane perpendicular to the magnetic field of 0.25 Tesla. The rod velocity vector and the magnetic field vectors are mutually perpendicular. Okay, so the rod is moving perpendicular to the field. Calculate the magnetic force on the electrons in the rod. Okay, so the direction of the force is V cross B. V, when you turn from V to B, the force will be upward, but this is a negative charge, so the force is downward. Magnitude of the force is QVB. A quarter of that is 0.4. 0.4 times 5 is 2. 2 times 10 to the minus 9. The electric field in the rod. Okay. How do we calculate the electric field in the rod? We know what is the potential difference in the rod. EMF is the electric field times the length of the rod. That's equal to BLV. Okay. So the electric field is B times V. So what does this tell you? the electric field. If the rod were 1 meter long, the voltage difference would be 1.25 volts. You want a 2.5 volt battery, you take a 2 meter rod. The potential difference between the ends of the rod. Okay. So see, the potential difference between the ends of the rod is E times L, 1.25 volt per meter, times what is the length of the rod? 25 centimeters, 0.25 meters. So 0.62, 0.31 volts. What is the speed of the rod if the potential difference is 1 volt? You want it to be 1 volt, B is 0.25 Tesla, and length is 0.25 meters. Okay. So this 1 over 0.25 is 4, that's 4, so this is equal to 16 meters per second. Okay. Calculate the induced electric field in a 50 turn coil with a diameter of 15 centimeter that's placed in a uniform magnetic field of magnitude 0.5 Tesla, so that the face of the coil and the magnetic field are perpendicular to each other. This magnetic field is reduced to 0 in 0.1 second. Okay. So magnetic field goes from 0.5 Tesla to 0 in 0.1 seconds. Okay, so oops. The induced EMF is del phi by del T, equal to del by del T. N is the number of turns of coil, B times area. Okay. So the magnitude of the induced EMF is NB. Okay, and that is equal to the electric field times the length of the coil. What is the length of the coil? So you have 50 turns of the coil. What's the length of the coil?
Circumference times 50.
Yep. Okay, so it's electric field is N times 2 pi R equal to N times pi R squared times del B by del T. So the electric field is, the radius is 7.5 centimeters. And the magnetic field goes to from 0.5 Tesla to 0 in 0.1 seconds. And what should this mess of units work out to? Meters, Tesla, or second? What is that equal to? Volt per meter. Volt per meter. That's the electric field. So this is 5, and that's 2.5. So 2.5 times 7.5. 15 and 3.75. 18.75 to 10 to the minus 2 volt per meter. Okay. The current through a long solenoid with n turns per meter and radius r is changing with time given by di by dt. Calculate the induced electric field as a function of the distance r from the central axis of the solenoid. Okay, here's a long solenoid that's carrying current. What does a solenoid do? So
Looks like a donut.
that's a toroid. This is just a cylinder, a solenoid. Okay? It produces a magnetic field like that. Okay? And the point of saying a long solenoid is excuse me, the field right outside is 0. Okay? So the field is confined there. On the edges, the field will go like that, but we're not concerned with that. Okay? What they want you to find is calculate the induced electric field as a function of distance r. Okay, we're going to calculate the field there as a function of distance r. Okay, so you're going to increase the current through here. That means you're increasing the strength of the magnetic field. So what will be the direction of the induced current?
It'll increase as the magnetic field increases.
So if the magnetic field increases, what you want to do is the induced current to produce a magnetic field in the opposite direction. Okay, so it'll be, the induced current will be in this direction. Okay. All right. So what we have is E dot ds around that closed loop equal to minus d phi by dt. Inside a solenoid, the magnetic field is given by mu naught n I. Okay. And we'll call this area A. Okay. This electric field is constant, so this guy is E times 2 pi r, where this is r. Okay. And this area is pi, we'll call this area A equal to pi r squared. R is this radius. So E times 2 pi r equal to d by dt of B times area guess mu naught A N di by dt. So E is mu naught A N 2 pi R di by dt. So this is the electric field if you're outside the solenoid. It falls off as 1 over R. Okay, the electric field. And we said that the further out you are, the weaker the electric field. Okay? And it's related to the rate of change of current. So if the current is steady, if this is 0, the electric field is 0. Why is the electric field 0 if the current is steady? There's no change in the magnetic field and that won't induce any. Okay, so you want a time varying magnetic field. Okay. So this is for the outside and you can calculate this, and if you can put I equal to that and calculate that. Now let me do it. Calculate the electric field induced inside and outside the solenoid. So we'll do inside the solenoid. Okay. Let's see what changes. So we'll call it 50 part B, inside the solenoid. Okay, so you're producing a magnetic field. And now if the ring is inside the solenoid, this is R. Now the flux is this area. Okay, the flux through this loop is this area. Okay, and so E times 2 pi R equal to d by d phi by dt, d by dt of B times area equal to d by dt of mu naught n I pi r squared. Now this area is just this area, okay, pi r squared. So E times 2 pi r equal to mu naught n I pi r squared di by dt. So now E equal to mu naught n R by 2 di by dt. So inside the solenoid, the electric field increases the further out you are, okay, linearly with R. And you can plug in for I. Okay, so I won't do that. The current in a long solenoid of radius 3 centimeters is varied with time at a rate of 2 amperes per second. A circular loop of wire of radius 5 centimeters and resistance, so the solenoid is 3 centimeters and the current loop of radius 5 centimeter and resistance 2 ohms surrounds the solenoid. Find the electric current induced in the solenoid. And so here's the magnetic field. The current in the solenoid is increasing at 2 amps a second. So this is the solenoid, the current is increasing, the magnetic field is increasing. So what is the direction of the induced current? Okay, so that'll be the direction of the induced current, okay? Because you want to produce a magnetic field in the opposite direction. All right, so we already, from the previous problem, we are outside the EMF. The EMF is mu naught A N di by dt, okay? So the EMF is E times that, okay? Which is that. So the EMF is all right, I'll do it D. The current is what's changing. So, and the induced, well, okay, well, the induced current, we'll give it a different color. The EMF divided by the resistance. Oh, bad notation. We'll have to call this little r. A is equal to pi r square. Because I want the big R for the resistance. So it's mu naught n pi r square divided by the resistance di by dt. This I is the current in the solenoid. This is the induced current. Okay. So the induced current is mu naught n pi r square divided by the resistance and di by dt. Mu naught is 4 pi times 10 to the minus 7 Tesla meter amp. N is N is not given. Okay, so we'll have to make up an N. So there's a problem with this thing. Let's call it 1,000 per meter. Okay, Okay, so I made up N. Okay. Pi. The radius is 3 centimeters. And di by dt is 2 amperes per second. And the resistance of this outer loop is 2 ohms. So that's the induced current. That's 10 to the 4, 10 to the 11, 10 to the 8, amperes. And then you have 4 pi into pi into 9, and this 2 cancels with that 2. So the induced current is okay, 4 microamps, 3.55 microamps. A flat square coil of 20 turns that has a side of length 15 centimeters is rotating in a magnetic field of strength 0.05 Tesla. If the maximum field, okay, so this is the kind of fields that are generated in a generator. That's the that's the strength of these magnets. 0.05 Tesla. That's about 100 times stronger than the Earth's field. If the maximum EMF produced in the coil is 30 millivolts, what is the angular velocity? So you saw that Emax is, okay, let's look at the expression. There's NAB omega. Okay, a flat circular coil of 20 turns, that's 20. Length, so area is L square. What is the angular velocity of the coil? Okay, so angular velocity is Emax. And A is L square B. (30 millivolts). N is 20 turns. L is 15 centimeters. 15 into 10 minus 2 square. That's 10 minus 3, 10 minus 4. So that becomes, you get a 10 there. And then this is 10 minus 2. And that becomes 10 to the 3. So this is 30 into 10 to the 3 divided by 20 times 15 square divided by 5. And per second will be this will be radians per second. Okay. Did I do that right? 10 to the minus 3 minus 4 minus 1. Oh, this is minus 2, 1. So No, I had it right. That's -3, 4, and 2 minus 6. That makes it 10 to the 3. Anyway, I hope I did it right. You guys can check, okay?